Today's experimental math seminar speaker is our very own George Spahn, who will talk about counting maximal seat assignments that obey social distancing. As usually, you're welcome to ask questions anytime and unmute yourself. Otherwise, please mute yourself. Thank you.
Thank you. Yeah, so my name is George. I'm a fifth-year PhD student. Dr. Z is my advisor. And this was joint work with him. And the intent for this talk is that it should be very accessible. So if I say something confusing and I don't say, this is just too confusing, I'm going to move on rapidly, then please just interrupt me and I will be happy to say more about it. Okay, so the initial context here is, let's see, the slide title is being a little bit hidden, but it's fine. If you're proctoring an exam and you don't want two students to sit next to each other, you might write on the board, for example, no two students sit horizontally adjacent or vertically adjacent. You might wonder exactly what kind of density of students you can actually fit into the classroom. Now, surely if you enforce a checkerboard pattern and actually go physically move people, then you can get 50% density, but maybe the students just sit sort of randomly without violating the rules. And you might ask, will we run out of space and what kind of density can we expect? Right, so as input, we have the dimensions of some grid of seats, R rows and C columns, and we have a set of forbidden patterns S. So this is just saying like no two horizontally adjacent, no two vertically adjacent. And a seating assignment can be represented as a matrix. So the ones are occupied seats, the zeros are empty. And an assignment is said to be maximal, right, if it satisfies two properties. Basically, you can't fit any more students in without violating the rules. And of course, the rules are not violated yet. So as an example, the one on the left has 8 ones and is not maximal. On the top row here, you can add another 1 without violating the rule.
Yes.
But the one on the, yes? Is there a question? The one on the right is maximal, and it only has 7 ones, so you can be not maximal and have more ones. Oh, so the questions we're interested in, given the rows, columns, and the set of forbidden patterns, what is the maximum and minimum possible densities of a maximal configuration? How many maximal configurations are there? If we were to select a maximal configuration uniformly at random, what is the expected density? So that's what we'll be looking at next. So first question, what is the maximum density? So this is pretty easy. Here you can see the checkerboard pattern gives a density of 1/2. And this is sort of what you might be hoping for. If the total amount of seats is odd, it can be slightly higher than 1/2, but
I probably missed something. How pattern is given?
The forbidden patterns is currently no two horizontally adjacent and no two vertically adjacent. We haven't formalized we'll talk about other types of patterns later and in general to an arbitrary pattern, but
thank you.
Yeah, this is what we have for now. So you might guess that the min density might be a little bit similar, but imagine you're proctoring and the students are sitting like this. It sort of looks like you should be able to fit more people in there, but actually you can't. So here the density is only a 1/4. Can we go smaller? Yeah, so for every 1, you could theoretically put 4 zeros around it. And that chunk of 5 squares has a density of 1/5. And you can tile the plane with these T or cross pieces, as you can kind of see in the bottom picture there. So the limiting density should come out to be 1/5 as the sizes get bigger. But in small sizes, you'll have more ones along the edge. So for example, if we limit ourselves to only 4 rows and just look at the number of columns and looking at the minimum density, it will never drop below 1/4. Just because you have to have ones on the top and the bottom too much. With 5 rows, we require at least 21 columns to get a density below 1/4. And with 6 rows, we only require 15 columns. So I looked at my code and I noticed that there are only 2 ways to do 6 rows, 15 columns in under 1/4. So this is a puzzle I posed to some of my friends online, is if you have a 6x15 grid and you want to place 22 x's that satisfy the property, then how can you do it? And this is one of only 2 solutions. There's also a vertical reflection. And my friend was able to solve it. And I was very happy about that. Okay, so now we want to talk about how to do this counting automatically. And so in general, we are going to restrict ourselves to a fixed number of rows. It's just a little bit too hard for an n by n grid. So we're just going to say r rows, and then consider the sequence counting the number of maximal assignments as a function of the number of columns. And an assignment is just a sequence of columns that satisfies some local conditions. And so if you're familiar with any of my previous talks, you might expect what I'm going to do, which is the finite state machine approach. So if you don't know what a finite state machine is, it's basically a directed graph. The edges are called transitions, and they're labeled with symbols from some alphabet. And the vertices are called the states, and those are used to store information. And then some of the states are accept states, and if a sequence of symbols leads to an accept state, then the word formed by the sequence of symbols that brought you throughout the graph to that accepts point is said to be accepted. So just as an example, so here the input is a binary string, and so you'll start at A, and then you'll start reading in 0s and 1s, and you'll move along this graph. And if you end up at A, then it's an accepted string. And if you don't, it's not. So does anyone see what type of purpose this finite state machine might do? So what is it actually checking for? It's a hard question, maybe. So this one checks if for divisibility by 3, you write the digits in normal in the normal ordering, and then whenever so if you are in 0 mod 3 and you get a 1, then you go to 1 mod 3. If you get another 1, it sort of cancels out and you go back to 0 mod 3. And similarly, you can get over to 2 mod 3. Anyways, it's just an example. So for us, oops, I turned off my monitor screen by accident. The symbols are going to be the possible columns. So we really want to be reading in a sequence of columns from our assignment. And each of those columns is going to tell us where to go on the graph. And so there's r rows, so there'll be 2 to the r possible columns each, because there's only 0 and 1 in the matrix. And so there's 2 to the r possible symbols in our alphabet. And so an R by C maximal assignment will be an accepted word consisting of these symbols of length C. So for C columns, we need a length C. Yeah, so there's two ways that you can fail to be maximal. You either have two adjacent ones, or you have a 0 with no adjacent one. Right, so you can either be violating the condition directly, or you can fail to be maximal. And a 0 with an adjacent 1 is said to be a satisfied 0. If we encounter an unsatisfied 0, we should reject. So it's pretty easy to check if there are two adjacent ones. If you read it in a column that has two adjacent ones in the same column, you just immediately reject. And then you can also store the contents of the previous column in the state. And then you can check whether the one that you just read is next to one of the ones in the previous column and reject if that's the case. And if a 1 is adjacent to a 1 that we haven't read yet, you might worry that shouldn't we reject? Well, we can just reject when we see the other one that's coming later. Detecting unsatisfied zeros is a little bit trickier. We don't have enough information to determine whether a 0 in the current column is satisfied because we don't know the future. So instead, we will check that the zeros in the previous column is satisfied. Now, in order to do that, we actually need to know even the column before the previous column. So we need to store the previous two columns in the state. And if we do know the previous two columns and we know the current column, then we can check that the previous column, every 0 is satisfied. Right, satisfied just means that there is a 1 next to it. And so it's not a violation of maximality. So if we're storing two previous columns in the state, then that's 2R entries of the matrix, and so 2 to the 2R possible states. Questions? Right, so here's an example. We need to check that the... Yes.
This is an upper bound, right? You don't have usually all 2 to the power 2R.
Yeah, in practice, these states are not used, a lot of them. Good point. Yeah, just then as an example here, this 0 forces a 1 here, and then that will force a 0 here and a 0 here. And this has to be a 0, so it doesn't add in two adjacent ones. And so we have a state going from, these two previous columns are stored in the state, and then we have 0, 0, 1, 0, and now these two columns are being over here. And so we label this edge, 0, 0, 1, 0. And if we receive anything else, then we must reject immediately. Questions? So when are we done? When can we accept? So if we reach the end of input, we can't just accept because we still need to check the zeros in the most recent column to see if those are satisfied. But if they all are satisfied, then we accept. So here's what it will look like for R equals 2. As you can see, most of these state, so with R equals 2, we have 2 columns stored in the state, so a total of 4 binary numbers, so 2 to the 4 equals 16 states. And you can see that most of them are not used. They just have violations in them or other reasons don't work. And there's sort of 6 alive states here, and each one has either 1 or 2 arrows going out of it. So remember that. It will come up again. And so now if we're trying to count...
So what was the start state in this automata?
Yes. The initialization is omitted. So eventually you'll get into here, but there's some garbage you have to go through at the beginning to even get there.
Mm-hmm.
The code deals with this, to be honest. I didn't look into what it does too much.
Okay.
But basically, you have to do some initialization, and then eventually you're in here. But that's a good question. All right, and also we're going to now go from the accept states and just have one big accept state. So we'll have some sort of end of input symbol, which does that combining for us. And yeah, so each maximal assignment corresponds to a path from start to accept. And the number of maximal assignments with C columns is the number of paths from start to accept with length C. So now we can count paths. And so this is called the transition matrix method. We let M be the adjacency matrix of the state machine. So each state becomes a row and column of the matrix. So it's a big matrix with one row for each state. And a valid transition from I to J is represented by a 1 in the ijth entry of M, and all other entries are 0. So M squared of ij, right? So this is the ith row of M times the jth column. The ith row tells us every way that you can leave state I, and the jth column tells you every way that you can enter state J. And so the ones that line up there are going to contribute to the dot product, and those will be exactly paths of length 2 from I to J. And similarly, the cth power of M will now count the number of paths from I to J of length C, which is very nice. And so once we can construct this matrix using the code, we can compute the sequence. So for 2 rows, this is the sequence we get. Does anyone notice anything about it?
Well, you didn't list the
That's twice Fibonacci number.
Yes. What were you saying, Neil?
I said you didn't give the A number for it in the OEIS.
True. But it is there. Yeah, this is twice the Fibonacci sequence. And so why does it satisfy the Fibonacci recurrence? Well, first, we can give a nice, easy explanation of this. So first, you can't end with 1, 1 because that's a violation. And you also can't end with 0, 0 because in order for those zeros to satisfy, you need a 1, 1 in the previous column. So say without loss of generality, you end with 1, 0. If you end with 0, 1, well, that's why it's 2 times the Fibonacci sequence. And now this is kind of like a leapfrogging question where you count the number of ways to climb the n steps where you can only take 1 step or 2 steps. So the previous columns can either look like this or like this. You can either directly switch which row the 1 is in, or you can have a break of zeros first. So if you haven't seen the sort of leapfrog question before, it's counted by the Fibonacci sequence. The number of ways you can end here is the number of ways you can end 1 shorter plus this, and the number of ways you can end 2 shorter plus this. Okay, so for what about 3 rows? Here's the sequence. What about 4 rows? Here's the sequence. These are in the OEIS. You can take a second to look at it, but you probably won't have anything to say.
But not for this reason, right? For different reasons.
Yeah, so why are they in the OEIS? So let's take a look at the OEIS entry here for A157049, which is the 3 by n case. So this is the number of n by 3 0-4 arrays with each element equal to the number its horizontal and vertical 0 neighbors. Okay, so we're looking at grids with 3 rows, and the entries in these grid are from 0 to 4. Each 0 is adjacent to 0 zeros. Does that seem familiar? Yeah, that's kind of similar to our 1s, which are not adjacent to each other. And each other grid location is the number of zeros that are next to it. And so that is uniquely determined by where the zeros are. So if we were to create a bijection, we would just replace all the non-zeros with zeros. But why is this maximal? Well, if you had a zero with no zeros next to it, it would be a failure of maximality if you had a zero with all zeros next to it. And so then it would need to be 4, which is a contradiction because it itself is 0. And another way to look at this, which is mentioned in the OAS, is that it's the maximal independent sets in the grid graph. So if you recall from graph theory that an independent set of vertices is a subset of the vertices such that no two are adjacent. And so we're basically trying to make a largest possible independent set where sort of the entries of the grid are vertices and they are connected by edges with their adjacent neighbors. The maximal independent set of an arbitrary graph is denoted alpha of g. And in general, computing alpha of g is hard. For an n-vertex graph, the best known algorithm takes O of 1.2 to the n. So it's strongly NP hard or something like that. Okay, so what about the generating function? So it's actually pretty easy for us to get the generating function for this sequence. Yeah, so for the sequence, it's just the nth power of this matrix, and then you look at a specific entry. And the generating function, you just multiply by x to the n. If you haven't seen generating functions, you basically just treat the sequence as coefficients of an infinite power series. And then we can set up a nice system of equations to find the generating function. So for each node, the number of ways to get there in n steps is equal to the number of ways to get to the preceding nodes in n-1 steps. So we have a separate generating function for the number of ways to reach state I in n steps. And we're going to say that's f sub I. And so then f sub I is equal to the sum over all the adjacent nodes of x times f sub j. And this x times f sub j, it just multiplying by x basically just shifts the generating function, or shifts the sequence offset by 1. And Maple can solve this system very easily. And there's also a nice shortcut. So if we ignore matrices, then you could kind of think, you could write it like this: f of x equals the sum of m to the n, x to the n. And then if you use the formula for a geometric series, then this is 1 over 1 minus mx. And so then, well, what if we just replace the 1 with the identity matrix and we take the inverse instead of dividing? And so this matrix actually contains all of our desired generating functions, which is pretty cool. So if we call this matrix n, then n, 1, 2 gives the generating function for the number of paths from start to accept. And so here it is for r equals 3. And in the OAS, it's currently listed as an empirical generating function, but this should provide a rigorous proof. Okay, so now let's talk about density again. So what if we want to compute the average density over all these maximal assignments? Well, we can modify the transition matrix M. So previously it had entries either 1 or 0 if there were edges in the graph or not. And now we're going to replace the 1s with powers of z. Z is just some arbitrary weight variable. So z to the t will indicate that the corresponding transition between those two states involved a column that had t1s. So as we read in columns, we're adding 1s, and the power of z is keeping track of how many we've seen. So now we have density polynomials. So previously, m to the n1, 2 counted the number of maximal assignments with n columns. Now it's a polynomial in z. the coefficient of z to the k will give us the number of maximal assignments with n columns and k total ones. So let's look at an example here. So for 3 by 3 assignments, we get the polynomial z to the 5th plus z to the 4th plus 8z cubed. And so this z to the 5th is like 1z to the 5th, which means there's one way to do it with 5 ones, which is right here. And then this is the one with 4. And then there's 8 ways to do it with 3 ones. Here are 2 of them, and they each have 4 rotations. And that's it. So now we can compute the average density of all of these. And it comes out to 0.37. And one cool way that you can compute this is you take the derivative of g. So when you take the derivative of g, you are weighting each type. Like I guess like this one has 3 ones. So we're weighting the ones with 3 ones by the coefficient here, which is 8. So when you take the derivative, the 3 and the 8 will get multiplied, which is actually exactly what you want to be doing to compute the average. So you do g prime, and then you replace the z with 1. And then you divide by g of 1, which is the total number of configurations. And then you just divide by 9 to get the density. Questions about that? So the nice thing is that we can also include z in the generating function. So we can have a bivariate generating function. And so now the coefficient of x to the j, z to the k, will give the number of maximal assignments with j columns and k total ones. And so for 3 rows, this is what it comes out to. And Maple is great at extracting the coefficient polynomials of this. So if you want to know the series and the coefficient of x to the 5th, then you can just plug that into Maple and it will give you a polynomial in z. So that's how you would do it for 5 columns. And we can also compute the limiting density. I'm not going to get into this too much, but we can plug in z equals 1 and look at the roots of the denominator of the generating function and get some asymptotics. And we can take the limit as the number of columns goes to infinity. So for r equals 3, the limiting density is 0.352. And as r gets bigger, the limiting density gets a little bit lower, which kind of makes sense because you're going to have more ones on the edge. But it's only slightly smaller than the 3 by 3 case, which was 0.37. Okay, so what about other distributions? Also, let me just check how much time I have. Okay. Yeah, so far we have computed the average density, assuming a uniform distribution on maximal assignments. But there is sort of no reason that this is true for any model in practice, right? Students filtering into a classroom might obey some other distribution. And we can consider other models using simulation.
George, you disappeared. I can hear your voice, but I cannot see your beautiful face. Thank you.
Hopefully that fixed it. Sorry, my bad. Okay. So what if each student sequentially picks a seat uniformly at random from the set of available seats that don't violate the rules? So this is called random sequential absorption. And for now, for 3 by 3 grids, the average density is 0.44. So that's significantly higher than 0.37. Why? Well, here's one reason why. So here again, we're I mean, I only show 4, but there's 10 here with the rotations of the ones on the right. So this is the maximal 3x3 assignments. And notice that the middle seat is only taken once. So if we pick one of these uniformly at random, we'll only get the middle seat 10% of the time. Under sequential absorption, the first person to walk into the room has an even higher than 10% of just sitting there right away. And if they do sit there right away, then we are automatically forcing the maximum possible density, which is 5 out of 9. And that's not even counting for people potentially sitting in the corners and then the person sits in the middle later. And so basically the maximal assignments, once you start sitting in a checkerboard, it's really easy to force the rest of the checkerboard. So there aren't that many different choices. So under the uniform distribution, it won't be weighted that much. But under the sequential, it's very easy to wind up in the maximal or the max density configuration. In fact, it's just as easy to end up in any type of distribution or any type of arrangement for the first few people that come in. Yeah, so basically, if the first people come in a sparse way, then there's many choices later on. And if they come in a checkerboard way, there's few choices later on. So that's why it will be higher. So we also ran a simulation with 100x3 matrices. And the average density came out to 0.394, which is notably higher than the limiting density under the uniform distribution, as the number of columns went to infinity, which was only 0.35. So now I'd like to generalize S. So remember that S is the set of violations. And so far, we've only looked at the specific case where S has 2 elements, the horizontal adjacencies and the vertical adjacencies. And we'd like to represent these violations as polyominoes. They don't really need to be connected, but it's kind of a nice visualization. And it's easy to represent these in the computer as just a set of coordinates. So we can do non-attacking kings. If we also prohibit diagonal adjacencies, then this is the famous non-attacking kings problem. And these sequences are also in the OEIS under the maximal independent set of the king grid graph, it's called. Grid king graph or something. And the next one I want to talk about is housing development.
Hey, George, sorry to interrupt. I think it's only up to 4 by n. The 5 by n case is not there yet. So if you're a good guy, you should enter it when you have
the 5 by n king case?
Yeah, I think so.
Sure, yeah. And we do have generating function for that. Yeah, so another one is housing development. And so the paper that inspired this research was called Packing Density of Combinatorial Settlement Planning Models. And they were interested in avoiding this T-piece. And the reason is that when you're building houses, you kind of don't want to block in any house from having no windows of access to the sun. And apparently there's no sun in the north. And so we only care if the east, west, and south are all blocked, then that's illegal. So that gives rise to this T-shaped piece. Yeah, so how do we deal with these arbitrary patterns in the code? So it's not sufficient just to only keep track of the previous 2 columns. And we set W, capital W, to be the largest width of any of the polyominoes. And to avoid adding that polyomino, we need to know the previous W-1 columns. And that will, if we do know those columns, we can make sure that we are not adding in any of that polyomino. But in order to check maximality, it's not quite enough. So for the downward facing t piece, what in order to check a zero, like this zero, we need to know some stuff on the left of it and some stuff on the right of it to see if it's satisfied. Because it could be the rightmost zero of a t-piece, it could be the leftmost zero of the t-piece. If either of those happen, it's good. So what we need to do is we store the 4 previous columns, and then we ensure that the zeros in the 3rd column are satisfied when adding the most recent column. So as we add stuff over here, we go back 2, and now we have the 4 previous columns in the state, and we can check that this 0 is satisfied. So in general, we need to store the previous 2w minus 2 columns. The reason it's minus 2 is because there's the 1 overlap here, and then we also don't need to count the most recent column. And that gives us a total of 2 to the r times 2w minus 2 states. And again, the code will eliminate a lot of these states right away. So it's not actually that many states, but yeah, most of them are unusable. So for the downward facing t, we get this following sequence, which is not yet in the OAS, but we should add it. And sadly, we weren't able to get the generating function, or at least I wasn't, of this sequence. But what we can do is we can rotate the t to make w smaller. So what about the right-facing t? So what if we want to maximally avoid this t with r equals 4? Then we get the following sequence. And this is in the OAS. And it satisfies this very nice recurrence, which is you just multiply that previous one by 3, and then you add the 2 previous one. And I don't know really why this is happening. And so I would like to pose this as a challenge, is to give a combinatorial explanation of why with 4 rows and you try to avoid this right-facing t maximally, then it will have such a nice recurrence. So if you discover something, you should shoot me an email or something like that, and I'd be very interested.
And I hope you'll add your comment to that sequence, because that's interesting.
Yeah. Yeah, I definitely will. Good point.
Well, and the same thing for all the OAIS entries that you've mentioned. If they come up in your work, it's only it's good for everyone if you put a note in saying that it arose in your context.
Sure. That would be a nice thing to add, I agree. And then the last thing I want to talk about, let's see, how much time is there? Okay, maybe I'll end a little bit early, but the last thing I want to talk about is sort of a generalization that I'm interested in working on as kind of a community project for anyone else that's interested in a type of problem similar to this. And so basically, the general type of problem is we're counting 0 to 1 matrices that satisfy a given set of properties. And this can come up in a lot of different ways. For example, in the past, I did Baxter matrices, and we did some enumeration of New York Times puzzles. And so the finite state machine approach is well suited to tackling many of these problems. And so what I want to do is abstract the code so that if you have some problem and you can phrase it as counting rectangular arrangements of something, and you're interested in fixing the number of rows and seeing some data about the sequence of as you vary the columns and solving for a generating function, then really all you should need to do is be able to describe what the set of states is and a way to compute the transitions between those states. So the states contain some finite amount of information about the columns seen so far, such as the contents of the previous 10 columns. For the gerrymandering sequence, which was joint work with Manuel Cowers, we needed to keep track of some finite connectivity data about the different rows. And so basically any way to, if you just need to keep track of finite amount of information for a fixed amount of rows, then you can encode that into the state. And so if you're a user to this sort of abstract code, you'll need to just say like a function that will return the set of states. And data can be in any format you want. It just needs to be hashable. So basically we can easily tell when two states are the same. And the set membership is very fast for hashable data. Basically, when you compute the transition, then you can look up the indices for the right rows of the matrix quickly. That's the purpose of that. And then the transition function can just be, the user can implement it using whatever kind of states they had made, and they just need to return, 1 if it's a valid transition or 0 if it's not. They can also store some weight in a variable. That also works. And then have Maple do the rest. And I hope that maybe this will be useful to other people working on similar research in the future. And yeah, that's all I wanted to talk about. So yeah, I'll end a little early.
Thank you, George, for a great, very, very lucid and fascinating talk. And we have plenty of time for questions. Anybody has a question for George?
Yeah, actually, I have a comment to make. And
Yes.
sorry, George, and I came late, but anyway, so whatever I saw was very nice. And but I have a comment to make because of actually it's Ian Yauslin made that, and I'm just forwarding that comment to you. We had a seminar talk by Gene Spear today in a mathematical physics seminar. It was about a facilitated exclusion process on a lattice Z to the D. Okay, so you and it's you can only hop from one side to a nearest neighbor side. So but you when it's unoccupied and it's either 0 or 1 basically. Okay, but the facilitation means you can only hop if actually at least one of your neighboring sides is occupied. So now when you think about, and that is Ian Yauslin's comment about how students can fill into a classroom and they come in, randomly sit down, and then you announce, hey guys, it's social distancing. You have to, there has to be some chair between you and the next person on the side. And so, if you don't have any neighbor, you don't need to move, no? But if you do have a neighbor, you must move. But you can only do if any neighboring seat is also unoccupied. And the question is, where does that lead to? No? So I wonder whether you can think about your problem with this dynamical setting. You start somewhere with some initial state, and then you try to see where does it lead to. Do you end up with a perfect social distancing until it freezes, so to speak?
So we could easily describe the set of ending conditions for that process using some local rules, and then, use this method to count the number of ways that you could end and keep track of some statistics about those setups. I think that would be very doable.
Okay.
Yeah, that's a good project.
Very good.
More questions to George? So George, is a general framework that you are proposing. So it'll be very easy for anybody to use with like a Maple package.
Some kind of Maple package where they need to fill out a couple of the functions. So like you download the code and then you need to fill out a function called generate states and just return whatever you want. And then the code will make a matrix, and then you also need to fill out the matrix.
Sounds good. It'd be very useful for many people.
Yeah, so the function to fill out the matrix can just input 2 of the elements from the set of states that you made and output, some, it could really be anything. It just needs to output a 1 or a 0.
That's a good
I had a question. So what is fundamental problem that drives you to restrict to fixed number of rows? Why don't you can?
It's because that's what we can do, I think. So when we don't have a fixed number of rows, then this method doesn't really work very well.
No, the number of plays goes exponentially.
That's but this looks very similar to walks on lattice, right? You just have extra conditions, so you allow step up if neighbors are like different, 0, 1, right, or 1, 0, and you do not allow step 1 if they are both ones. So is it related to walks on lattices, enumerating the?
Well, the walks are kind of a sequential data, and I guess we don't really care so much about...
Yes, no, this is transfer methods that have been used to do, to study so-called self-avoiding walk. So the general case is intractable probably, but if you restrict it to a strip of a fixed width, not too wide, then the same technique could be useful.
Oh, yeah, okay. Self-avoiding walk would be perfect.
Thank you.
Are there any natural problems about tilings with polyominoes that sort of grow out of these considerations you've been thinking about?
I don't think we've done any pure tiling problems, although I imagine you could.
Okay.
In the past, we did some... It was like counting the number of spanning trees of the grid graph, something like that.
Thank you.
But I imagine that would work well.
Any more questions to George?
George, I want to ask something. So these densities you showed, do you have any hypothesis about the limiting density when you have maybe infinite number of columns or fixed R?
Yeah, we can fix R and then compute the limiting density. Where was that? Yeah, I didn't exactly go into the math of how we do it, but step 1 is we have this bivariate generating function. And so this counts the densities so the coefficient of X is telling us how many columns, and the coefficient, or the power of X is telling us how many columns, and the power of Z is telling us the density, basically. And so we can plug in Z equals 1 and look at the roots of the denominator, and then that can be used to compute some asymptotics of the generating function. And I don't exactly have the details right here, but it's like residue calculus.
It's an algebraic number always, but very complicated usually.
And then we did compute some of them. So these are limiting densities here. For the proctoring case, where we're just avoiding a horizontal and vertical adjacency.
And you can have as many decimals as you wish. You get 1,000 decimals. It's just slide. But it's still open to get the exact values for the random sequential adsorption, except for the one-dimensional case. So that'd be interesting.
Mm-hmm.
Right.
Any more questions? Well, thanks, George, for a great talk, and I hope to see you all in 2 weeks. The next speaker is Peter Olver from University of Minnesota. We'll talk about the late Allen Tannenbaum's contributions to computer vision. Hope to see you in 2 weeks. And Robert, please end this session. Thank you very much all for coming. Bye-bye.
Thank you. Bye.
Thank you.
Thank you.